In this video, I will be solving the second part of the first problem of UPSC Indian Forest Service 2025 Statistics Optional Paper 1. So, check whether f of x is a cumulative distributive function of a random variable x. So, in order to check a cumulative distribution function, so we must check the defining properties of a CDF. So, generally a CDF is defined from real numbers to the domain to the range 0 to 1. So the first condition that we have here is limit x tends to minus infinity, f of x is 0, and limit x tends to infinity, f of x is 1. So that means like for x is less than 0, so we have like f of x is nothing but e to the power x by 2. So that means like if you find limit x tends to minus infinity f of x, so that is nothing but limit x tends to minus infinity e to the power of x by 2, which is nothing but 0. And similarly for x greater than or equal to 1, we're having f of x as 1 minus e to the power 1 minus x by 2. So that means limit x tends to infinity f of x is nothing but limit x tends to infinity 1 minus e to the power of 1 minus x by 2. So that is nothing but 1 minus of 0, which is nothing but 1. So that means the first thing is satisfied, that at minus infinity it is 0 and at infinity it should tend to 1. And the second property is f of x is right continuous. So we have to check like whether this particular f of x is satisfying this right continuous property or not. So if we check here, like the potential points of change is at x is equals to 0 and x is equals to 1. So therefore like we can check whether it is right continuous at 0 and 1. So limit x tends to 0 minus f of x is e to the power 0 by 2, which is 1 by 2, and limit x tends to 0 plus f of x is 1 by 2 and f of 0 is also 1 by 2. So that means it is right continuous at 0. In fact, like it is continuous at 0. And in a similar way, limit x tends to 1 minus of f of x, so that is half. And f of 1, if we find, that is 1 minus e to the power of 1 minus 1 by 2, which is 1 minus 1 by 2, which is 1 by 2. And limit x tends to 1 plus f of x is anyways like 1 by 2. So that means f is right continuous. In particular, it is right continuous at 0 and 1, and everywhere else like by this particular formula. And the third property that it should satisfy is f is non-decreasing. So if we consider the function like for x less than 0, this f dash of x is e to the power of x by 2, which is greater than 0. So that means it is increasing on this interval minus infinity to 0. And similarly for 0 less than or equal to x less than 1, f is constant. So that means it is nothing but half. And for x is greater than 1, we can see f dash of x is e to the power of 1 minus x by 2, which is greater than 0. So that means like it is increasing on 1 to infinity. So the values are matching at boundaries. So that means like we can clearly see that f is non-decreasing on this entire real number space. So f is non-decreasing on this R. So all properties are satisfied. So f is a, so therefore f is a valid CDF. So in fact like we can also give the corresponding density function. So the corresponding density function will just be e to the power x by 2, e to the power of x divided by 2 when x is less than 0, 0 when 0 less than x is less than 1, e to the power of minus 1 by 2 when x is greater than 1. So that is the density function. And there are no point masses or jumps, so as like f is continuous at every point. So therefore like that's about the first part. Now if we consider the second part, like so for I is equals to 1, 2 and so on till n, let xi's be independent and identically distributed as n comma n mu normal mu comma sigma square, we need to show that the weak law of large numbers holds. So first, like we were given that this x1, x2 and so on xn, so that is following i.i.d normal mu sigma square. So if we define the sample mean xn bar, that is 1 by n summation I is equals to 1 to n xi. So expectation of xn bar is nothing but mu, and variance of xn bar is 1 by n summation I is equals to 1 to n variance of xi, which is n sigma square by n square, which is sigma square by n. So by Chebyshev's inequality, so we have by Chebyshev's inequality that like for any epsilon greater than 0, probability of xn minus mu greater than or equal to epsilon is less than or equal to variance of xn bar by sigma square. So as n tends to infinity, we can clearly see this variance of xn bar by sigma square is just sigma square by n sigma square, and this tends to 0. So that means this probability of xn bar minus mu greater than epsilon tends to 0 for every epsilon greater than 0. So that means, and this is exactly the weak law of large numbers, that xn should, in probability, it should converge to this mu. Right, so hence like we have proved that weak law of large numbers is holding here. So we can also see this like in another way. So when we are having a normal distribution, so we can also note that xn bar is exactly normal mu sigma square by n. So we can use this fact that variance tends to 0 to conclude that the convergence in probability. And yeah, but Chebyshev's like is sufficient like in general. So yeah, so that's how like we proved the weak law of large numbers holds in this following case. So that's it for this video. We'll meet in the next video.